Today's lecture is on potential energy and specifically a quantity called the electric potential. The electrostatic field and the gravitational field have a lot of similarities, and since we know a lot about the gravitational field, we'll review what we know and use that and apply that to the electric field. If we have an object at point A in a uniform gravitational field and we move it to point B through some random path, then we know that the gravitational field will do some amount of work on the object. That work can be calculated by the force of gravity times the distance that it travels. But the distance that it travels doesn't depend on the actual path distance, but it depends on the height difference. So the work is then calculated by mg times the distance d. As we move the object from point A to point B, it's going to reduce in potential energy. At point B, there's less potential energy than point A. So this amount of work can be seen as a negative change in the potential energy. Okay. So now let's say we have an object that starts at point A in a uniform electric field. So there's a uniform electric field. We can take some path to get from point A to point B. The work that's done by the electric field is calculated also by the force of the electric field times the distance. In the last lecture, we saw that the force from the electric field is just the charge times the electric field, and the distance that's going to travel is d. So again, this distance is only the distance, the vertical distance from point A to point B. Similarly to the gravitational field, this can be seen as a negative change in the electric potential energy. We are now going to define a quantity called the electric potential. The change in electric potential, V, is equal to a change in potential energy per unit charge. The units of this electric potential are joules per coulomb, which is also more commonly known as a volt, capital V. In a constant electric field, we can calculate the change in electric potential as just the electric field times the distance in which you move the object. Now this equation is great for constant electric fields, but we know that around the spherical objects, the electric field is not always constant. Just like around the spherical mass, the gravitational field is not always constant. So let's say we start with our spherical mass, capital M. We know that there's a gravitational field that's exerted on a little mass. So if we were to bring this little mass over to a new point, then there's going to be some change in potential energy. Now, the universal gravitational potential energy equation is negative G, capital M, little m, over R. Okay. So we can do something very similar when we have electric charges. So we start with a charge Q1. Q1 has an electric field that extends in space and exists at a point where we have a second charge Q2. We can now define our electric potential energy as K Q1 Q2 over R. Now this equation is just like the gravitational potential energy equation, except there's no negative sign. So in the gravitational potential energy equation, the negative sign represents an attractive force. So that as you bring the small mass closer and closer to the big mass, then the gravitational potential energy gets smaller and smaller. Now, because electrostatic force can be both attractive and repulsive, then the case where you have an attractive force is when either Q1 or Q2 is negative and the other one is positive. If one of them were positive or negative, then the negative sign would naturally come into the equation based on the sign of each of these charges. Now, if we move Q2 to some other location, then it will have a different distance away from Q1. Let's call that R sub B. In doing so, we will have changed the electric potential energy. So the change in electric potential energy would be given by KQ1, Q2 over R sub B, the final position, minus K Q1, Q2 over R sub A, the initial position. That would give you the change in potential energy. If we want the electric potential, then we would just divide this guy by Q2, and in doing so, you would get rid of the Q2 on both sides, and this would give us our change in electric potential. So delta V is equal to V at point B minus V at point A. What this tells us then is that we can define the electric potential at any point by that relationship there. So the electric potential V is given by KQ over R, and this is the electric potential around a point charge. In the diagram, I have labeled my point charge Q1. Okay. What's really nice about this equation is that K is a constant, Q is the charge, and it's a scalar value, and this R is also a scalar value. It's just the distance between the charge Q1 and whatever point you want to calculate the electric potential at. So the electric potential is really a scalar quantity, and that makes a lot of calculations a lot easier. So let's revisit this problem that we had yesterday, where we had 2 point charges equidistant from the central axis. So, and I'll label these distances again. That was our D, that was the D. The length along the axis is x, and if I want to calculate the electric potential at this point over here, then what I want to do is calculate the electric potential, the contributions from each of the charges. Since electric potential is a scalar quantity, we don't have to do any of the fancy vector addition stuff, and we can actually just calculate this as K Q1 over R plus K Q2 over R. Since our distance R is the distance from the charge to the point, so it's that distance and that distance, then, and both of them are the same, I can factor some stuff out, and I get K over R times Q1 plus Q2. This is great because Q1 and Q2 have the same magnitude but opposing signs, so this summation is going to be 0, and our electric potential at that point is exactly 0. So now I'm going to introduce a concept called the equipotential surface. And what that means is it's a surface with equal electric potential on that surface. So the electric potential from a point charge is given by V is equal to KQ over R. So for a fixed distance away from a charge, you're going to have an electric potential. So there's some amount of electric potential here that you would calculate by multiplying KQ times R. Now the distance at each of these points out here is exactly the same, so all of these points will have the same electric potential. And I can draw the surface. If you imagine this in 3 dimensions, this would be a sphere surrounding our charge Q. Every single point on the surface would have the same electric potential. Likewise, if I were to make a larger radius, I can make a larger radius sphere surrounding it, and each of the points on that circle would also have equal potential. What this means is that if you were to place a charge right there, and you wanted to move it to another point on the surface, right? So you move this charge from point A to point B. Okay? Because they have the same electric potential, and electric potential is just the amount of electric potential energy per coulomb, then we're effectively saying that they have the same exact potential energy at points A and point B, which means that it will require no work at all. There's no change in energy to move along an equipotential surface. Now I can draw the electric field around this charge Q, and we know that the electric field extends radially outward because it's a positive charge. So it's going to go like that, or it will go like this at points in between. And what we notice anytime we draw these electric field lines, so there's a very unique relationship between the electric field lines and these equipotential surfaces, and that is that an electric field line is always going to make a right angle with an equipotential surface. And that is a rule. So equipotential surfaces are perpendicular to electric field lines. There's one more fact about equipotential surfaces, and that has to do with metals or conductors. Any metal or conductor are equipotential surfaces. So if you have a metal shape, so some random metal shape, as the weird bean thing that I've drawn here, what we're saying is that if there were a charge on the surface and you wanted to move this charge around, it would take absolutely no energy to do so. No work to move these charges around. And this is something that's really important to remember, is that the potential, the electric potential, if this point is at 10 volts, then any other point on this metal surface also has to have a potential of 10 volts. All right, that's it for today's lecture. I'll see you tomorrow in class.